Right now, millions of servers are running, processing search results, writing code, and answering queries. But it comes with a massive cost that nobody puts on the invoice: electricity. A ChatGPT query uses 10 times the power of a Google search. Multiply that by 1 billion queries a day, and AI is quietly draining the grid.
To understand the energy crisis, we must look at the scale of what we've built. Hundreds of massive data centers span the globe, from Microsoft in Virginia to Google in Iowa. Compute requirements for training major AI models have been doubling every 6 months. Training GPT-4 alone consumed 50 gigawatt hours. That is the annual energy use of 50,000 American households. Training is just the beginning.
So where does all that electricity go? Inside a data center, it starts with the GPU, but computation itself only accounts for 40% of total power. Another 35% is wasted on cooling to keep the hardware from melting. And while model training creates a massive one-time energy spike, inference, every query you make, runs 24/7. And that constant hum is getting louder. Behind all this code is physical infrastructure: steel, concrete, and copper. A single modern AI data center can consume up to 500 megawatts of power. That is enough to run the entire city of Buffalo, New York. And we are building hundreds. Construction spending is skyrocketing, with U.S. data center electricity demand projected to more than double by 2030.
The electrical grid is a fragile patchwork of networks built 50 or 60 years ago. Normally, it balances supply and demand in real time, but AI data centers draw constant, massive power. This overload causes transmission lines to overheat, leading to regional brownouts. PJM, the largest U.S. competitive market, now has a 12-year waitlist for new connections. Electricity demand is projected to rise 20% by 2035. The demand curve is AI. The supply curve is everything built before it. The grid can't keep up.
AI companies make bold commitments about clean energy and carbon-free goals. But in Virginia, the data center capital, grid emissions are rising for the first time in decades. Dominion Energy is reactivating retired fossil fuel plants to meet the new demand. Google's total greenhouse emissions grew 48% in just 4 years. Microsoft's rose 29%. Voluntary carbon pledges simply aren't matching reality. Electricity isn't the only resource at stake. AI has a massive water problem. Evaporative cooling systems in data centers consume between 1 and 5 million gallons of fresh water daily. Even a 20-question chat with ChatGPT evaporates 500 milliliters of water to cool the servers. At scale, that's 500 million liters evaporated every single day. And the irony? We are building these massive hubs in water-stressed deserts like Phoenix and Las Vegas.
Can renewables save us? Solar and wind are making progress, but they have a mismatch problem. Solar peaks for 6 hours, wind varies, but AI compute runs 24/7. This intermittency gap is filled by fossil fuels because battery storage is still a decade away. Nuclear power provides continuous, zero-carbon electricity, prompting tech giants to sign reactor deals. But nuclear projects take over 10 years to build. The AI boom is happening now. AI optimists point to efficiency gains. Computation requires less energy per task year over year. But history warns us of the Jevons paradox. Making steam engines more efficient actually increased coal use. As queries get cheaper, we run hundreds of billions more of them. In 2022, 1 billion queries cost thousands of dollars. Today, it's a fraction of that. Efficiency improvements are real, but they are completely outpaced by exploding demand. So where does this end? The choices we make right now will decide our future. On path 1, business as usual. AI electricity demand consumes 10% of the U.S. grid by 2030. Globally, infrastructure is scaling rapidly, powered largely by fossil fuels like coal in China and India. On path 2, managed growth, we enforce strict carbon pricing and fast-track nuclear energy. On path 3, crisis mode, we face regional grid failures, utility price spikes, and compute throttling.
There are no international frameworks. The conversation must start now, before the lights go out.